Hey guys, Mr. Betts here. So in this example, we've got another Lagrange error bound, and this time we're approaching it from a different perspective. In the level one example, we had an approximation and a certain number of terms from the Maclaurin polynomial that we were going to use. We wanted to know how accurate that was. Now we want to approximate sine of zero point 0.4, and we want to make sure that our approximation is within a certain error bound. So what I want to do here is we're just going to assume that we're using a certain number of terms. We're going to assume the degree is let's say n, and then we're going to set up an equation so that we can solve for n. So I do want to point out that in the last example, we were approximating sine of 0.1. So when we were plugging into the formula, we were plugging in 0.1. Now we're going to be plugging in 0.4. So we're moving further away from the center, which means our answer is going to be less accurate, and the Lagrange error bound formula will account for that for us. So our error is going to be bounded by, and I'm going to refer to the error as r sub n, and this is for 0.4. This is going to be, the absolute value of the error is going to be less than or equal to the maximum possible value of the next term, or the next derivative. So the nth derivative, I'm saying that sine of x is f of x here. So the n plus first derivative of sine evaluated at some point, and that point is going to be somewhere between 0 and 0.4. And then that's going to be times 0.4 to the nth power, n plus first power, sorry, over n plus 1 factorial. So again, this is the general form right here of what the n plus first term would be in a Maclaurin polynomial. The difference is that we don't know the c value here. It's somewhere between the center and 0.4, and we want to plug in the value here that's going to make this the biggest. And to do that, we just plug in the biggest value for x on that interval, which is going to give us the biggest value here. So what we want is we want this to be less than 0.001. All right, so this expression right here needs to be less than 0.001. In the other example that I did, I mentioned this also, that sine and cosine, and negative sine and negative cosine are all bounded between -1 and +1. So in general, the simplest way we can handle the maximum possible value of any of those trig functions, sine or cosine, this is always going to just be 1. Now, that's only going to work when we're dealing with sine or cosine. If we're taking derivatives of something else, then this is going to take a little bit more analysis, and we'll do some examples with that also. But with sine and cosine, things are pretty simple, and we just know that they can't be any bigger than 1, so we'll put 1 in there as a maximum possible value. So what we're looking at here then is this expression right here, 0.4 to the n plus 1 over n plus 1 factorial, is less than 0.001. Essentially what we're going to do here is we're going to do trial and error. So we're going to plug into our calculator different values for n, and evaluate this expression, and we want the smallest value of n that gives us an expression here that's going to be less than 1/1000th. So I want to show you a little trick that you can use in your calculator. So remember, the expression here is 0.4 to the n plus first power over n plus 1 factorial, needs to be less than 0.001. So what I did here is I typed in that expression with n in there, but before I did, I typed in 3 stored for n. So by putting 3 in for n and then putting a colon here, it's going to evaluate this, and then it's going to evaluate this, and it's going to tell me what the answer is. So with n equal to 3, our error is going to be bounded by close to 1/1000th, but it's a little bit bigger than 1/1000th. So then what I can do is just on my calculator hit second enter, and that's going to put this expression back on the screen, and I just replace the 3 with a 4 and do it again. Now when I did that, I got 8.53 repeating times 10 to the -5th. So if you think about what that means, we're going to move the decimal to the left 5 places. So 1, 2, 3, 4, 5 decimal goes there, and that expression right there, that number is clearly less than 1/1000th. So 4 is going to be our answer. So this method right here is really a trial and error method, but it is going to be a calculator problem if you have to do something like this. So you can kind of take advantage of some things that your calculator can do by storing a value for n and then evaluating that expression with n in there instead of the number itself. Of course, you could also just type into your calculator 0.4 to the 4th power over 4 factorial, and then type it again and just replace the 4 with a 5, and that works also. One other thing I want to point out, if you need the factorial in your calculator, you want to go to the math menu, and then you want to go to the probability menu. So factorials are commonly used in probabilities, so the quickest way to get there is math menu and then the probability menu.